Hello! Today we will be going over Lab 3, Physics 2212 on DC and RC circuits. The purpose of this experiment was to predict the behavior of circuits containing resistors in parallel. Also, use multimeters to measure the actual values of conventional current and potential difference in circuits. And finally, to examine the behavior of ohmic resistors and capacitors. Some of the physics fundamentals that we used in this experiment were the conservation of energy, also known as the loop rule, that says that the delta V of a round trip is equal to 0, the conservation of charge, which is also known as the knot rule, that says that the current going into an area must equal the current exiting the area, and the concepts of Ohm's law, potential difference of a capacitor, and capacitance of a capacitor. For the first part of the experiment, we used a very simple circuit in which we had two batteries connected to 2 ammeters and 2 resistors in series, one of 47 ohms and the other one of 100 ohms. You can also see on this slide the relevant formula that we used to make all calculations that we will be describing in the following slides. The relevant formula that I wanted to point out is the last one, the formula for RC, which is a formula that was given specifically for this lab to calculate the time dependence on a discharging capacitor and calculating the value of RC, which in this experiment was of 6. For the first part of the experiment, we had to take the simple circuit that we were given and use the simulation CCK to run it. In this case, we had to calculate the current going through the circuit which was of 0.020 amperes, and this was the same for both ammeters. We also had to calculate the current when this was in a backwards format, when the ammeters were just connected in opposite ends and the value for the current was exactly the same. And we used a voltmeter to calculate the difference in voltage in different parts of the circuit and be able to calculate the overall voltage, let's say volt loop. And you can see in the slides the values that were obtained for the batteries, for the resistors of 47 and 100 ohms respectively, and finally the value for the loop, the voltage for the loop was of 0. Taking the results that we saw in the previous slide, we could make a graph to kind of see a whole perspective on how the potential changes as we go through the circuit. The wires do not affect the potential, the resistors decrease the potential, the batteries raise the potential, and the ammeters also do not affect the potential, and we can see that it starts at a 0 and it ends as well at a 0. After doing the first part of the experiment, we could answer the following questions for discussion. So, why doesn't the ammeter reading change when attaching a voltmeter? This does not change because the voltmeter has very high resistance, so that means that very little current flows through it, and that makes no change in the reading for the ammeter. Also, what happens to the current through the other ammeter that is placed in parallel with a 100 ohm resistor? That ammeter had a reading of 0.6, and that means that the current increased. And the resistance that we calculated for the different resistors as well as the wire and the ammeter, you can see it in the slide, and we use that by rearranging Ohm's law. That means that we just took the ratio between the voltage, the difference in voltage, over the current. On the second part of this experiment, we tested charging and discharging capacitors. So we first connected a battery, a 9-volt battery, with a light bulb, one of 10 ohms and the other one of 20 ohms, as well as a capacitor. And we charged the capacitor by connecting it with the battery, and then we discharged the capacitor by taking out the battery and connecting it directly to the light bulb. In this, we saw that at first, in both cases, the light went bright and then it became dimmer and dimmer. That means that at first the capacitor was being charged, and when the battery was taken out, the capacitor was being discharged. And you can see that it took more time for the light bulb to go dimmer when we used a higher resistance light bulb. After doing the demo, we also calculated the time dependence on the capacitor and how much time it took for it to charge and discharge, and we did this with a 30 ohm light bulb and calculating different points in time for the difference in voltage, and we saw that as time increased, that voltage decreased. And in this case, the graph is not perfectly decreasing just because the time points that were taken were very separate from each other. To linearize the equation, we took the logarithm of the difference in voltage with the first time point, and you can see that the voltage just decreases as time increases. To finally calculate RC, we took the slope of the graph and we took the inverse of this value, which gave us a value of 3.22, but the experimental value gave us 6. This is still close enough, but the human error was that we took different time points very far from each other. That did not make the data consistent and give you a more closer value to 6. For the what if questions, if a real ammeter would have been used in real life, that means that the current would have been lower because the ammeters have a resistance to it, but in the perfect model we assume that they had zero resistance. And for the second question, the ideal model will predict that the charge would be instant and a large current would have been able to flow in the model, but in real life there is a resistance, so the capacitor would have not charged instantly.